won't be live, but this will be on YouTube soon.
All right. So, like I said over there, my name's Cody. Work over across the street at Podium. I really enjoy distributed systems. I got my start building a failed service detector and a few other things in Erlang at a platform as a service company that competes with Heroku. And so early on in my career, I was just immersed in this, we have to get these things done with super low latency, we need lots of availability and replication, you know, a lot of the problems that we face in distributed systems. And it's interesting to see the trade-offs that Google made in doing Spanner, where they chose to emphasize latency, where they chose to emphasize throughput, where they chose to emphasize consistency over availability. And it was really awesome that they published a paper explaining a lot of the infrastructure and design decisions behind their database. So first off, Spanner, what is it? Like all tech databases, like all the databases there are, it has a super descriptive name, right? You know, something like Postgres or Oracle that tells you exactly what it does and what trade-offs it makes, right? So first off, it's intended to be globally distributed. It is operating on Google scale, which, you know, if you take Twitter scale and multiply it by another couple thousand, that's Google scale. The big features that the big thing they were trying to do was to have synchronous replication across multiple data centers. So Google made Bigtable, which was one of the things that really kicked off the NoSQL movement in the late 2000s. Curse you, Google. And a lot of their developers found a pain point that they wanted a more consistent database. Now, consistency here is not the same as in ACID consistency. It is consistency in the sense of the CAP theorem. So, you know, the CAP theorem is one of those buzzwords that people talk about, but people don't really understand. They'll say, oh, this is highly available, and then Jepsen will say, no, it's not. Or they'll say, hey, it's highly consistent, and Jepsen will say, no, it's not. So when they're talking about consistency, they are talking about linearizability. That as events are going through, as transactions are happening, they are consistent in the sense that they look like they have happened in serial order, or in linear order. It uses Paxos to do replication, and it started as a KV store, key value store, but evolved to include a lot of semi-relational features. So what do I mean by semi-relational? You'll see. One of the other things was they wanted application-level developers to be able to specify their constraints. Just because my application needs to be distributed across 10 data centers, that doesn't mean yours does. So their goal was configurability of how many data centers and which data centers for locality and latency. And the other main thing that they spent a pretty good chunk of time describing was their timestamp abstraction. Normally, you know, you think of a timestamp, it is 1,736,000,000, you know, that many milliseconds since Unix, or since 1970, right? Well, their API directly exposes clock drift or time uncertainty. And as a result of that, they're able to do lots of really cool things that he is going to be able to talk about. All right, so I talked about the linearizability before I intended to, but this is from a paper called Highly Available Transactions. Lynch and a few others, or Fisher and a few others, I forget, you know, they start mixing authors up. They discovered that linearizability is incompatible with availability in the CAP theorem. Another paper, Highly Available Transactions, went beyond just looking at serializability and talked about which things were highly available versus not available, and others which are kind of in between. And so linearizability is the one that was emphasized in Spanner, meaning that this is a strongly consistent distributed system rather than an eventually consistent or highly available system. So for high-level architecture, the big overarching deployment of a spanner is a universe. At the time of writing, there were exactly 3 universes in the world. That sentence sounds nonsensical, but that's what it is. One was development only, one was production and development, I'm assuming a sort of staging, and a third was a worldwide production only. So when you're deploying your application, you're not deploying an instance of Spanner, you are deploying a logical instance within this universe. And that a universe is comprised of zones. Within any given data center, you will have one-to-many zones. These zones are kind of the unit of replication. So if something is replicated, you want it in this zone, which is in this data center, and in this zone, which is in this data center, and in this third zone, clear over across the continent for just in case those other 2 go down. Within a zone, you've got a master node, you've got hundreds to thousands of span servers, and the relationship between them is that the zone master assigns data to specific span servers. So that's where partitioning happens. Before I continue, I'm moving fairly quick through this. Are there any questions? Okay. So now we can talk about the span server is where the bulk of the paper is, like of the section that I'm covering at least. This is where a lot of the replication, a lot of the different guarantees are made, what the structure of the database and the data model looks like. So any given span server, which there are hundreds to thousands of within a given zone, is responsible for hundreds of tablets. Again, consistent with all databases, that is a super descriptive name. The idea behind it is that it's a mapping from a key and a timestamp to some bytes.
Probably a protocol buffer.
Yep, knowing Google.
Sorry, you said it is a mapping? What is it again?
A tablet.
A tablet is a mapping.
Yep, it is a bag of these mappings, a bag of these key values.
Okay.
So, some implications here. You have your key and your timestamp. Therefore, the same key can have multiple versions. So that's why this goes beyond the key value store and into a what's called a temporal multi-version database. So each of these span servers, or each of these tablets, has a single Paxos state machine, or member of a Paxos cluster, which is responsible specifically for the state of that tablet. And Paxos clusters replicate these across multiple zones.
How many people weren't here for our Paxos thing? So just briefly.
I was just about to pull out the computer, but go ahead.
Just briefly.
Paxos is a protocol for implementing distributed consensus. So if you have a whole bunch of machines and they need to agree on something, for example, you have a database system and you want them to agree on which transactions have succeeded. What is the state of the database? This is built on top of this is the idea of the atomic commit, or a distributed commit, which is the main thing that it's used for. Well, the most well-known thing that it's used for.
The benefit of Paxos is it means that as long as a majority of the nodes in the cluster are up, the entire cluster can continue to make progress.
Yep.
So it's nice in the sense that it gives you fault tolerance, but still, being able to.
Mm-hmm. It makes a bunch of really cool guarantees.
Yeah. Nice.
And so each of these span servers are members of this cluster which spans multiple zones. Now again, these zones some zones might be in the same data center, but the point is that at least 2 of these zones will be in different data centers for fault tolerance. And that's just a graphic showing that we'll cover this dir stuff later. But where there are multiple zones, this group spans multiple zones. So data gets replicated across the world. So directories. Like a lot of, it would be really annoying if you made a user one key and I made for my application a user one key and they clashed. Collisions are no fun in key value stores. Anyone who's done stuff with Redis and forgotten to prepend keys knows what I'm talking about. So on top of these tablets, so the tablet is a bag of mappings. On top of these mappings, Spanner has directories. The paper goes out of its way to say, yeah, that's really kind of a bad name for it, and that it should be called a bucket. So if you've used Reoc or any similar key value stores which have namespacing built in, that's what a directory is. In about 5 minutes, we will see how this directory and tablet structure work together to provide the guarantees in the data model. So a directory is the fine-grained spot where we can say this directory belongs in this data center, or this directory belongs here. And when you're at Google Scale, you don't want someone making a search request having to go get data clear over in Europe from Utah to come back, right? You want that locality so a user who constantly accesses his data from Utah can have stuff within a few hundred milliseconds rather than going all clear across the world. And so the data model, we use these directories and these mappings to provide a really unique data model. In some ways it is similar to a relational structure, in some ways it's similar to a key value store, and in other ways it's kind of similar to like a hierarchical database. So yeah, semi-relational tables. What that means by semi-relational, we'll see in a second. But the nice thing about it is that these tables have a schema. It's not like a columnar data store, like Cassandra, for example, where this row has these columns, but this row may or may not have the same columns. There's no guarantees in a columnar data store. And Bigtable was much the same way. For Spanner, a table is a table, and it has a set of columns that it must have. It has a SQL-like query language. They said it's basically SQL with a few extra extensions. And the other important thing, when you're dealing with NoSQL databases, a lot of times transactions start getting a bit tricky, right? There's just a lot of people looking off elsewhere. Anyway, so it provides transactions, including distributed transactions. So you create your database within whichever universe, probably the production one, and it can contain any number of tables which have rows, columns, and version values. So it's very similar in this sense to a typical relational database that we're very used to using. But it's not purely relational. Rows have to have names, which makes it closer to a KV store in some senses. Each table has to have an ordered set of one or more primary key columns. Now, you hear that and you say, well, actually, that's not very dissimilar from Postgres or Oracle or MySQL. You know, my table has a primary key. Well, what's the surprise here? Well, each table defines a mapping from its primary key columns to its non-primary key columns. And it must be partitioned by the application into a hierarchy of tables. Yep?
What's the difference between a row name and a primary key?
In this case, it's basically the same thing.
Okay.
So does that essentially function as an index then?
Yep.
Okay.
Oh, well, as a primary key. So
yeah, because you're saying they map to a different table. Is that?
the columns
Yeah.
map to other columns.
Yes. Okay.
I've got an example on the next slide, so that might help. So in the paper, they give this example of users and albums. So A user has a user ID of int64. It's required. A user has an email, and its primary key is the user ID. An album has a user ID, so similar to a foreign, kind of similar to a foreign key here. It has an album ID and a name for the album. But now you look, the users has a primary key of the UID. The albums has a primary key of the UID and the album ID. And so the albums, you see this hierarchy here. If you've worked with Mongo, you might have seen similar structures. So you have a user and his associated albums in a given directory. So rows which belong together, which are often accessed together, should be in the same directory. That way they're in the same location for quick lookups. Because it would not be pleasant to go, oh, here's a user wants a list of all of his or her albums. Here's the first one. Oh, well, better go all the clear over to Minnesota to get that second one. Wouldn't make a whole lot of sense to do that. And so by putting these together in this directory, we get fast lookups. Now, so album 1 here belongs to user 1, UID 1, and album ID 1. This mapping of the two columns will map to the name of the album. So
or any other columns that were added after that, right?
Yes.
Okay.
So it's kind of a key value store, kind of a relational thing, kind of a hierarchical database. It's just kind of weird and kind of cool. So this directory abstraction gives very quick lookups because data that's looked up together should be located in the same place.
Seems like it's a reverse ORM. You're overlaying the relational structure on top of that
Beforehand.
a key value store
Yeah.
representation.
Yep. And so it started out like Bigtable as a key value-ish thing and evolved to include these semi-relational features, including a SQL-like query language, which we saw an example of here. And I'm not sure how you would do queries on it for the non-primary key columns. So it looks like, to me, you have to look it up mostly by primary key.
So a quick question on the albums. Does that mean that you can only look up the album based on a user ID and an album ID?
I can't answer that, not really knowing. Yeah, I just have not seen anything about how they would query based on other columns.
Well, like a relational database, if you don't have an index, you're going to have to do a scan.
Yeah.
And scan through all of the values.
Index is required.
An index is required to do an efficient lookup.
Could you
It
add
would
a
probably be an external
that's
index.
probably off topic. Could you add a second primary index on it that's just album IDs?
I'm assuming that if they have index support, that's how they implement it.
Thanks.
Right. So that's the basic architecture of Spanner.
Sweet.
We're going to jump into kind of the crazy concurrency control of Spanner that guarantees ACID compliance on a worldwide scale using GPS clocks and crazy stuff. I will start by saying I am the least qualified person in this room to get this.
That's what user groups are for.
Exactly. I am a distributed systems wannabe, not yet.
Everyone here is a distributed systems person because you're here.
Yeah, there you
Yes.
go.
Um,
Best way to learn something is to try to teach it. So
That's true.
You know, that's what they say, and I'm still not getting it. Still lost here.
You were thrust into an academic paper there. And
I was. So I took that belief, and I volunteered to JT to do this. And then I was like, I am way over my head. This is
It's okay.
far beyond what I expected. So,
then you have really like even just what will be considered distributed systems.
Yeah.
So like your backend software, front end,
Yeah.
different environment.
If you talk to the gun DB people, they'll tell you that very thing.
Wait, what?
There's a company that sometimes some of their developers come. They have what they would say.
Good afternoon.
Sorry.
Okay.
They say what?
I didn't mean to interrupt you there.
They say they have talk to the servers, talking to the clients, and so on. It's a distributed system.
You can consider like the cache coherency protocol inside your CPU that deals with the different processor cores accessing memory to be a distributed system.
Or
On a small
texting
scale.
your family members.
Yeah, there's lots of things that
Did you get my last
distributed
text? My last text?
applies to.
Yeah. All right.
So that's why I want to understand it, but I don't yet. So I will.
It's not like one thing that you can just understand. It encompasses a lot of stuff.
Yeah.
Even if, there's some basic principles at the core of it.
So I'm going to approach this a little bit differently. I don't have a talk prepared that I'm going to teach these principles because I don't fully understand it myself. So my hope is we're going to use a couple of different presentations given by some of the Spano guys and just a few chunks out of that. And I'm going to do my best to relay what I understood from this section of the paper, which was very little. And then I'm hoping that we can diagram some of this on the whiteboard and understand it at a deeper level than I do. If I can start to understand this with you guys, then everyone in the room will be able to understand it. Because I think I'm the lowest common denominator here. So not to be self-deprecating.
Sounds like a fun approach.
Yeah. So both of these guys in their talks talked about this desirable property of having serializability in your database to provide a consistent external view of events, external consistency. So that any given application, any given client will see the same outcome from the events. Not necessarily in the same order, the same exact order, but the same logical order, that the outcome is the same. And that's how they achieve this ACID compliance worldwide. So they begin and go right into timestamp management, talking about, well, actually, backing up a little bit, before the paper even gets into this, it talks about this idea of a true time. And because there is no, because different servers across the world will necessarily have different clocks, they will never be in perfect synchronization.
Oh, I read about that. They install like little antennas on top of their data centers.
Yeah, so they basically have GPS receivers and atomic clocks, and the atomic clocks are basically just there to make sure that the GPS receivers are doing their job and not too far off. So
implementing this this paper on our own became a lot more complex.
Well, no. This part, the clock thing is hard, but there is actually a team of ex-Googlers that are working on implementing an open source spanner called Cockroach.
Yeah.
So they don't use the true time thing.
They don't. Oh, okay.
The thing that true time gives is a big performance benefit.
Okay.
So I don't know how much we'll go into the true time thing, but I can kind of explain that. It's just essentially a shortcut, a way around having some additional messages getting passed that makes it much more performant. But
because they can make the assumption that the time is the same.
yeah, when you have these messages going back and forth between data centers where you globally distributed, this is a global database, and so latencies actually really matter at this scale. And so if you're just running in a single data center, you don't necessarily care too much about the penalty of a message pass. But in the case of Spanner, they care a lot, and so this clock thing allows them to eliminate some of the messages that they would have had to have sent otherwise.
Okay. So maybe JT, I didn't understand how.
Throw that one away.
Yeah, thanks, Bob.
Yeah, I work at the BTP time scale where the difference between clock frequencies is different.
That's never happened.
Nominally, the same clocks matters
Right.
a great deal.
Sure. Yeah.
Yeah, what about that, Phil?
So they define this like true time function, truetime.now, and then it has an earliest property and a latest. And I don't understand how you pick what the earliest and latest is.
So okay. So they have two different types of clock hardware. They have the GPS clocks, and they have the atomic clocks. And they've gone through and figured out the bounds at which those clocks can drift. They know within
So this is statistical significance.
they know within a certain amount of certainty that the time is definitely between this timestamp and this timestamp. They don't know exactly what the time is, but they know that the time is definitely later than this and definitely earlier than this. And that's all they'll say. The
That's
true time
awesome.
API just returns the earliest and the latest bounds.
And that's configurable by the application as well.
Yeah, and so what happens is over time, until they do these recalibrations, the amount of uncertainty starts to increase. So the true time API is returning these larger and larger time windows until it can recalibrate and make sure that it understands what the maximum clock drift is.
Now, for the open source version of this, I mean, couldn't they use the same concept and just have much wider error range?
Oh, absolutely. I don't know if they're doing that, but
So what if they calculate relativity
Did
into
their
this?
own Jepson test.
GPS time.
Yeah.
Does it really?
And what they found is you can get really good performance as long as you only require serializable
Right. Oh, yeah.
transactions. If you want to have high performance linearizable transactions, you do need a true time server.
Yep.
They have it as a flag, it's not turned on by default. But if you want to play around with it, they'll let you do it. They just say, don't expect to need good performance.
Yeah, that makes a lot of sense. And in fact, the linearizability is why true time they do that across their data centers is for that reason.
Okay, so let's jump to a piece here that hopefully will bring some clarity to some of that. Okay. So here he's going to describe. He's going to describe why kind of this concept of there is a universal point in time at which an event happens that the computers won't always be synchronized on, but that's what this.
So how are we going to provide these synchronized snapshots? Well, what we intuitively want is we want some notion of global wall clock time. That is, we want to be able to say, take a snapshot at this absolute time across machines, across data centers. Well, it turns out that this property is equal to a theoretical property called external consistency. And I'll repeat what external consistency means. It means the commit order in which transactions appear to have executed is equivalent to the order in which users can see the transactions executed. So concurrency control, when it satisfies this property, guarantees that users will see something consistent with what they observed. Well, this is actually a relatively tricky property to implement because it involves commit order, global wall clock time. How are we going to actually do this? So the intuition is the following. We're going to transform the problem from one of commit order reasoning to timestamp order reasoning. What we'll do is we'll choose timestamps for transactions such that timestamp order equals commit order. And then the problem becomes, how do we show that we achieve timestamp ordering of transactions equals global wall time order of those transactions?
Okay, I only partially understood that. Help me understand what is he talking about here? Like changing, because he's talking about changing the problem space from commit order to timestamp order.
Well,
I don't understand.
so essentially what you're saying, well, what this guy's saying is if you have a sequence of commits, if you can decide globally that that order is the same for everybody, then that property is what you want.
Right.
But there's a stronger property which is you want the commits to actually not get reordered from what the users actually requested. So you want the users to request the operations, and you want them to happen in the exact same order, assuming you had some large global perfectly synchronized wall clock.
Yeah, the wall clock is the key idea here, and it's called a wall clock because if everybody's in a room, they can see the same clock up on the wall. So you don't have a synchronization problem. You're looking at the clock on the wall that tells you exactly what time it is.
So to jump,
The idea of universal time.
yeah, so to jump a little bit ahead, obviously not all the computers can agree on a global wall clock because they all have their own clocks and they're all slightly wrong. But since we have this, we definitely know the time is later than this timestamp and definitely know the time is earlier than this timestamp. You can say if a true time window is definitely completely before some other true time window, or they collide, right? Two true time windows can either overlap or not overlap. And if they don't overlap, there is a definite well-ordering of those two operations.
And if they could be similar, then the database can simply say, oh, well, we're going to put this one first.
I don't recall what happens in that case. I think that's obviously more complicated, but yeah.
Okay, so I think I'm understanding. The idea is we want this commit order, and we're going to achieve that by tying a timestamp to a commit, or more accurately, a timestamp range in this case, right?
So you want the notion of a wall clock, and you can order all of your commits if there is a wall clock that everybody sees, and you can assign a timestamp to each commit. Then you've just collapsed the problem from ordering commits to ordering timestamps.
Yep. Okay, thank you. Let's keep going.
Well, how would we do this in a single machine? How would we assign the timestamps to transactions? Remember, we're using strict two-phase locking, so there's a point at which we've acquired all of our locks. And the intuition is that we want to pick a timestamp that falls in the interval of time during which we hold all our locks. So we acquire all our locks. At some time after that, we pick the timestamp s equals now. And then we later release our locks after we've done the work in the transaction. Okay, and we can pick any timestamp in that interval as long as it's before we release our locks.
So that was important right there from the papers. They talk about this two-phase locking, where you are acquiring locks, and then eventually you're going to stop acquiring locks and begin to release some of those locks. The timestamp must be between those two phases.
Now, why does this give us the properties that we want? Well, the two properties that we want, remember, are timestamp order equals commit order. And you can see that by the diagram on the top of the slide. Let's say we have two transactions, T1 and T2, where T1 and T2 conflict on the data that they touch. Since they conflict, it must be the case that the intervals of time during which they hold their locks are disjoint, because otherwise you wouldn't have serializability of your locking. Therefore, the timestamp of T2 must precede the timestamp of T1, since the orange intervals cannot overlap.
Okay, what did you just say?
So the red interval is the full operation, and the orange interval is the period of time when the locks are all held. And so what he's saying is because the locks are mutually exclusive, there can't be an overlap of the orange time windows.
So full operation meaning server receives this request for a transaction, does its thing,
does all the things,
waits until it gets all of the locks it needs.
Yeah.
Takes a timestamp somewhere in there, releases the locks. Yeah, and what's it doing here?
This is just a window of time.
Okay.
Yeah. The red time ranges can overlap, of course, because there's concurrent operations happening.
Right.
But you in this single machine case he's talking about, you would only want you don't want any overlap between the orange time frames.
Yeah. The two lines are labeled T's, so I assume those are both
T1 is the top one and T2 is the bottom.
So you've got two transactions that are happening at the same time. It looks like the T1 was
maybe
requested
a little
first,
bit earlier, yeah.
But T2 actually began executing first. It was able to acquire blocks first. It executed, and then it released them so T1 could get the locks, and then it could execute. But there's obviously a distinct ordering because they had to get the locks, and they couldn't get the locks if another one was overlapping.
I can tell you what that does right there. That's when it turns that data into JSON. That's what that's doing.
Protocol buffers.
Yeah, it's a protocol.
Yeah.
I think a key insight is the fact that this only matters if there's actually a collision, if they're actually operating on the same data.
Yeah.
And so in that, if they're not touching on the same data, then you don't have to do any kind of collision detection. You don't have to do any kind of figuring things out. It just says, which one had the lock first? That's the one that's first.
Great point. The other clip I have mentions that that if there is a transaction 3 here, well, he's got 3. There's a transaction sub I here that comes in that has nothing to do with this data. It can execute at any time and commit at any time. We don't care. It's not conflicting.
One other thing that Spanner will do in some cases is it'll get one of these time ranges for what time it is. It'll want to make sure that everyone else knows that this operation happened, and so it'll just sleep until the end of its time range. So like it's very clear that that operation has been committed based on the uncertainty that's known about the clocks.
Don't jump the gun.
Oh, sorry, I jumped the gun. Sorry.
So he's going to describe that next.
Oh, great, great. Okay,
the commit
I'll shut
wait
up. I'll shut up.
phase.
I'll shut up.
So we're still in. Let's see. We're kind of in the start. Assigning timestamps.
Now that was the first condition we needed to transform the problem from reasoning about commit order into the domain of timestamp order. The second condition we need is that timestamp order respects global wall clock time. And that, you can see it by the bottom picture. Let's say we have 2 transactions that happen to touch different shards of the database and they don't conflict at all. But we know that T3 finished before T4 started. This is the key property of external consistency, that if a transaction finishes before another one starts, somebody could see that ordering, and you want the system to preserve that ordering through concurrency control. And you can see by the sort of obviously that when we pick a timestamp that falls within the orange bars, we're guaranteed that the timestamp of T3 precedes the timestamp of T4, sort of by construction, because of the fact that we know the 2 intervals don't overlap. So this is the intuition behind how we're going to pick timestamps to guarantee external consistency of Spanner. How are we going to actually do this across machines, across data centers? Because the previous slide assumed we had some global clock where we just pick a timestamp from that global clock. So what we do is we depend on a system we built at Google called TrueTime. And I'll describe the implementation of TrueTime a bit later in the talk. What I want to get to now is sort of the API. And the API is simple. TrueTime is a global wall clock time that reflects uncertainty in the clock. And it reflects uncertainty in the clock in the form of an interval that bounds the absolute time at which you executed the now call. So what is guaranteed by TrueTime is that earliest is guaranteed to be a time less than or equal to the time at which the event of calling now happened. And latest is a time that's guaranteed to be at or later than the time of the event of calling now.
And it's guaranteed by atomic
That's
clock.
a very strong invariant.
Right.
This says that we are guaranteeing the bounds on time. And I'll talk about how we make that guarantee later. We'll refer to the uncertainty of this interval as epsilon. So the diameter of the interval is 2 times epsilon. And that'll be important later to remember that notation. So how are we going to pick timestamps given that we have TrueTime? Well, what we do is we acquire all our locks. We pick the timestamp S to be TrueTime.now.latest. That is, we pick a timestamp in the future that is guaranteed to be an upper bound on the actual time at which now was executed. So that guarantees that S falls in the interval with respect to the acquisition of the locks. How do we guarantee that S falls in the interval with respect to releasing the locks? Well, what we do is we wait. We slow down the system to wait out the uncertainty in the clock. So we call this commit wait. And what we do is we simply spin, logically spin. We don't actually sit there in a loop and spin. And we spin until tt.now.earliest is greater than S. So we wait out the uncertainty on the other side of the interval. This is called commit wait, and it should be noted that the average length of commit wait is approximately 2 times the average epsilon. We pay epsilon on the left-hand side of the interval, and we pay epsilon on the right-hand side of the interval. As I'll briefly describe later, epsilon tends to be in the range 4 to 5 milliseconds in the common case. So 2 times average epsilon is about 10 milliseconds, which is an important value because that's actually pretty low. It's on the order of the latency of a disk write. And that's important because we can...
Okay, so I want to go back there. Help me understand. I don't know where my
video control with.
I wonder how they estimate this epsilon in general. What's the method of estimating the epsilon?
I don't remember the details, like
What is epsilon?
epsilon is
Could be
the amount of uncertainty they have in their clocks.
Oh, why did they name it that?
That's a
math
math term.
Oh, I
It's,
was gonna
it's a common
Google that.
Greek letter for that.
For
kind of
small
thing.
values. For epsilon
a
is
range, right?
often used in math to determine some small amount of delta.
Oh,
Oh, yeah, delta. Small amount of difference between two values,
oh,
yeah.
sorry, do you guys have an access point?
Vivian Guest is, it has a captive portal, but.
Oh, I see.
Okay, so this was something I was still a little bit fuzzy on. So help me understand what's going on here. So we want to pick an S that is greater, that is bounded between tt.now.latest and tt.now.earliest.
No, they said S is tt.now.latest.
Okay.
They're not picking one that's
So-
in that range. They're saying that we're going to pick S is tt.now.latest.
So what's this arrow?
That's when they call tt.now.
Oh.
I don't
Gotcha.
know. I'm guessing.
No, I think you're right because the paper describes that. So tt.now is the moment that, let's see, it says, yeah, tt.now is computed when it receives the request.
Yeah.
And then it's going to pick a,
So they're saying we have this amount of uncertainty, and we're just going to say that S is the latest value.
and I'm still.
So you've got your local notion of time
Uh-huh.
that you can use to measure how much time has passed pretty accurately. You don't necessarily know that your absolute number of clock ticks that has passed is synchronized, but you know that your notion, the distance between those ticks is accurate enough at the scale you're using that you can measure periods of time very accurately. And so you're saying, okay, I have to wait this long to be sure that the time that I got is now passed, that I'm beyond the bound of it. And then you know that that time is whenever anybody gets that time, they've got that range, you've waited longer than that, the latest value it could be.
I think I'm understanding that. I'm missing it at a concrete level, like at this implementation level. tt.now.latest is the upper bound of my time.
All we know about tt.now.latest is that when I called tt.now, it was definite. If there was some hypothetical global wall clock, when I called tt.now, it was before then. It was before latest. That's all I know. I know it was after earliest, but before latest. And so latest is the absolute latest my estimation of my clock drift thinks that my clock could be.
Okay, so I have this interval where latest is up here and earliest is down here.
Yeah.
How?
And you call tt.now. What we're saying is we don't know
somewhere.
exactly when you call tt.now. It's in that range.
Yeah.
The latest that tt.now, like, okay, there's tt.now, but then there's also like time.now. Like you have your like local time module that's just going to return some seconds from Unix epoch or nanoseconds from Unix epoch, right? If you call now with the standard system library now method, you're going to get a timestamp that's inside of this range. Okay, and so what we're saying is we're going to pick the value that is the furthest possible one in the future that we know it could be. If there's any sort of confusion, our system, our hardware, is guaranteeing that it could be no later than this value.
That what can be done later?
The timestamp that I just got. I just got a timestamp.
So that the absolute value of your computer's idea of what time it is could be off by that range.
But no more.
But no, right.
Right. So if you did TT now and got your system time at exactly the same time, your system time would be somewhere in that range, but you don't know which way is the truth.
So
So you've got to wait till you're outside of the outermost one in terms of your local clock before you know that you've passed whatever time that you wanted to be passed.
essentially,
I think it's
essentially,
just called-
what we're doing is we're trying to get not a range, but a specific integer that we can use for ordering. And the specific integer we're going to use for ordering is the latest value.
And okay, so what just clicked for me, I was wondering, why are we waiting until TT now earliest is greater than that? We're waiting for the window to pass this point that I had picked.
Yes, yes, right.
So that-
we're gonna hang on to the locks until that sliding uncertainty window passes completely.
Yeah.
Yep, that's exactly right.
What do you find your answers?
Hmm?
The uncertainty window is defined by the uncertainty of your clock synchronization.
So
So-
in this case, Google has very well defined, they've implemented these GPS clocks all over, and they have run tests on them to define exactly how far off those clocks get at any point in
Like
time.
latency from the clock to the computer, or?
Like
Yeah,
clock
well,
away
that's
from
Drift
atomic
with
time.
respect to one another. No two clocks will tell you exactly the same time. I mean, they're correct within some amount, but physical changes in like the temperature of the clock or whatever can change the rate at which they count time.
Okay.
So they can drift a little bit with respect to one another, and there can be other sources of error in the clock. There can be error in just reading the clock.
I'll just read
There's
their.
lots of different sources of error in clock signals.
This is
just abound on all the errors that they're aware of.
here's the section of how they actually compute this, like from a physical perspective. So true time is implemented as a set of time master machines per data center and a quote time slave daemon per machine. The majority of masters have GPS receivers with dedicated antennas. These masters are separated physically to reduce the effects of antenna failure, radio interference, and spoofing. The remaining masters, which we refer to as Armageddon masters, are equipped with atomic clocks. An atomic clock is not that expensive. Blah, blah, blah. All masters' time references are regularly compared against each other. Each master also cross-checks the rate at which its reference advances time against its own local clock and evicts itself if there is substantial divergence. Between synchronizations, Armageddon masters advertise a slowly increasing time uncertainty that's derived from conservatively applied worst-case clock drift. So what they've done is gone through and measured all of the possible sources of clock drift, where clocks get slower, faster, whatnot. And then they've gone and made conservative estimates of what that worst case is, and then built that into their protocol to assume that in between synchronizations, that they're going to assume that drift is happening. So that's how.
Very tedious. They actually.
Very tedious. This is very tedious. They had a lot of people work on this.
Time's hard.
Yeah, 4 years, he said.
Yeah.
I actually work on a different time synchronization protocol based on IEEE 1588, or called PTP.
Great stuff.
So is that kind of defined more as a constant, or is it just something that's kind of like dynamically computed for each?
It's changing all the time.
Oh, okay.
But that is what true time will return.
Yeah. Yeah.
That's what the true time algorithm is.
Yeah.
So beyond the scope. Now I'm curious, like, where true time comes from. I'm just pretending I have this true time dot now. What gave me that true time?
But your system is synchronizing with these masters, and there's some sort of a protocol where they can.
Where I get the bounds for true time.
Yeah, you see, you compare how fast your local clock is advancing compared to how fast the master clock is advancing, and you can compensate for errors in your own clock. And as long as you're doing that frequently enough, and you know the bounds of your own local clock drift, you can get
Close
the
enough.
bounds of the actual wall clock time.
Right. Cool. Let's jump further in this thing. Oh, I think I'm there.
Locks. How do we guarantee that S falls in the interval with respect to releasing the locks? Well, what we do is we wait. We slow down the system to wait.
We're already there. We watch more. Okay, so he has this good example of what's going to go on here. Oh, and all this. This is all good stuff too. Watch that. Cool.
And that's important because we can actually overlap commit weight with real work. So commit weight interacts with replication, for example, in Spanner. Let's say we have 3 replicas, we acquire locks at one of the replicas, we pick the timestamp S, then we can start our consensus algorithm. We use Paxos, but you could use other consensus algorithms. And then we achieve consensus on the right, and then we check commit weight is done. And after that, we release locks. I've drawn the picture so that commit weight looks larger than consensus cost. But remember, we allow clients to replicate their data across the country or across the globe. So 100 millisecond latency to actually achieve consensus is going to far dominate the cost of commit weight in the common case. It should also be noted that replication has to be integrated with concurrency control here. For reasons I won't go into detail, we actually can't notify the slaves of the fact that we've achieved consensus until after commit weight. Commit weight also.
So I'm just going to pause because that just clicked for me where it didn't before. Just want to make sure everyone understood that. Does everyone understand why we don't really care about commit weight? Like, that's not really a costly thing.
Yeah, when you're talking about Paxos and all of the back and forth over the country to coordinate everything.
A combination of distance compared to the speed of light as well as the expense of the protocol itself. It's so huge compared to this latency that's equivalent to a disk write.
So because we have to achieve consensus within Paxos, that's almost always going to take longer than this time window anyway. And so we will.
They've done a really good job of keeping that time window.
Yeah, it's critical that their clocks are really well synchronized. Like if their clocks aren't well synchronized, then that might suck. But since they are so well synchronized, yeah, this all hangs together. The first thing they tell you with distributed systems design is avoid clocks. Don't use clocks. Clocks are bad. And it's amazing that they got away with all this by just being like, we're going to use clocks for everything.
Like that show, they had some good blog articles. One, why vector clocks are easy, and then they had a counter one from their the same writer. Why vector clocks are hard. Issues that come with them.
Yep, you can trick yourself.
Yeah, there's difficulties with any approach, but they can be overcome if you're persistent enough and
have a fire hose of money.
Yeah.
Is this complexity worth it though for what they're doing?
Yes.
Yes.
Like, is it something that's going to last that long?
Yes. Yes. This is a huge win for Google.
So I was thinking like the upkeep cost of that because you have to understand the.
They have thousands of.
I think we missed it in this talk, but this guy says this is now what contains their advertising data and their clicks. In other words, this powers Google. Like the core revenue of Google now is based on this system. So it's
which is way easier to maintain than all of their MySQL clusters that they use.
Yes. Yeah, they can run their store on this stuff
right.
now.
Yeah.
Okay, we have 2 more. Let's finish off with 2 more minutes of this to see his example here.
Commit weight also interacts with two-phase commit. We can overlap the work with for two-phase commit as well. So let's say we have 3 participants. Each of them acquires locks. Well, each of them picks a timestamp using the algorithm I described. The 2 non-query participants log their prepared messages. And then they're done logging their prepared messages. They send prepared back to the coordinator, and they piggyback their values of S on the prepared message.
This is all Paxos stuff, right?
Then the coordinator computes an overall S timestamp, does commit weight, releases locks, and sends a committed message which piggybacks the overall S value back to the participants, after which time the participants can release their locks.
I'm not sure.
So this overlaps.
If I recall correctly, there's actually 2 levels of consensus going on in Spanner. So I'm not sure which one this is. There's the high-level 2-phase commit that they're doing, which this is commit weight and 2-phase commit. And then there's the lower-level Paxos that they're doing. So as I understand it, this could be wrong or oversimplifying, but essentially writes happen essentially by doing 2-phase commit on top of, instead of individual nodes, 2-phase commit on top of Paxos clusters.
Two-phase commit is typically a bad idea to do because if one node goes down, you can't make progress in two-phase commit because you're just waiting, you're hung. But if your individual nodes are Paxos clusters, they're much higher availability, and so they can survive. They can survive failures. So essentially, if you pick a better Lego brick, you can build some really interesting things. So I guess what I'm saying is I don't know specifically if this slide is Paxos or their higher level two-phase commit, but there is definitely message passing happening.
That clarifies a lot for me too, because their paper talks about Paxos writes and spanner client writes, which are different. That's the two layers.
When a transaction touches only a single Paxos cluster, it bypasses the two-phase commit. When a distributed transaction touches upon multiple Paxos clusters, then one of those clusters gets chosen as the leader, the coordinator, as they call it.
The coordinator Paxos cluster.
Yep, and then its leader is called the coordinator leader, and its slaves are the coordinator slaves.
Oh my gosh. Like just think, like which one of the nodes in the Paxos cluster is responsible for sending the messages?
The coordinator leader.
I think these form nice abstraction layers, so you don't have to worry about which node at that level. You can say, okay, this Paxos cluster is a thing.
Just thinking about building
and I can
it,
operate on it like it's one entity.
Yeah, I still just want to
go
blow
down.
my brains out thinking about it.
Trying to manage.
Right.
And
These are some powerful Lego bricks.
And they said in the paper that the vast majority of transactions only touch upon a single Paxos cluster. So the two-phase commit is an exceedingly rare occurrence.
Which is probably still happening thousands of times a second.
Right, at their
Super rare.
Right, super rare. Just unbelievably rare. Only thousands of times a second.
The work of logging the prepare with commit wait. Note again that two-phase commit has to be integrated with commit wait because you can't actually send the committed message until you finish commit wait. Let me run briefly through the example of how this actually works with the data representation I described earlier. So let's suppose we have two transactions, one where we remove X from my friend list and myself from X's friend list. Well, let's say the two participants choose 6 and 8 for their timestamps. 8 gets chosen as the overall timestamp for the transaction, and then 8 gets propagated to the participant. And the write actually happens at 8. So we see in the bottom chart, at the timestamp 8 is when the removal of X as my friend happens. And then let's say the transaction 2 happens, and again, let's say it chooses timestamp 15 through the algorithm I described earlier. Well, then the post shows up at time 15. Now, this is the exact chart I showed earlier, but note that this uses true time to compute timestamps, and we can do this across machines, so this is across the green and purple shards. And the green and purple shards have consistent timestamps even though they're in different data centers. So,
okay, so this was another thing that I understood at a high level, but if anyone else grokked that better than I did, I'd love to understand this better. What's going on in this example here? So obviously he's talking about like I post, but I also remove my friend, remove myself from X's friend list. And then I post something about that friend. And I think that's the business case here.
The business case is posting a risky post about your friend. Perfect. Which, like, man, this is the kind of technology to take us to the moon or Mars or something, and we're posting risky things about our friends.
Yeah. So let me understand. So this is my transaction. I'll read that. We're going to see. Remove X from my friend list. What's going on here?
Okay, so there's.
So we have two friend lists, right? And we want them
Well,
both
yeah,
to stay in sync.
Yeah, you want to be out of your friend's friend list before you post your post, because your post shows up for your friend when you are a friend of them, and so that they see the post from their friends. So when you remove yourself from from that list by removing them from your list. That makes it so they don't see your risky post.
Okay, so this transaction, TC picked a start time
Of 6.
6.
But I guess we're saying that the transaction spans 2 different things. And so we're going to pick the later transaction. That's why S turns into 8 later. Is that a thing? I'm just saying words.
And I'm just nodding.
Cool.
Well, maybe it doesn't run the second one until it's finished removing. It does remove X from my friend list, then it does.
I mean, it must, right? That's
well,
the serializability.
You've got the white arrows in there saying that. I guess removing.
So this thing chose 8.
I'm puzzled by this S equals 6 on the top left.
Yeah.
And S equals 8 right under it. And then there's an S equals 8.
Yeah.
So that makes me think that.
I
What he was saying in the
don't know
video
how
was
this-
initially they both chose a time,
Right.
and because they differed, they just went with the second one.
Yeah, they go with the later of the.
But yeah,
Yeah.
But they go
That's-
with the later. That means this one tells it,
Yeah,
Okay, I picked 8.
my time window goes up to 8, and your time window went up to 6. Let's just go with whatever one's later because we can both just sleep and then it'll be fine.
it's
Yeah,
probably it.
I'm not understanding that.
So,
Sorry.
it's just a matter of the reason why all of the commit wait happens is just to make sure that the external view of what's happened is still lined up. So we're saying that, okay, so these 2 different groups are trying to do an operation, and we want them to appear like they happen atomically, right? So what timestamp does that atomic event happen? You could either pick the lesser of the 2 timestamps or the greater of the 2 timestamps. If you pick the greater of the 2 timestamps, then you know for certain that the lesser of the 2 one has also passed when the greater of the 2 has passed.
So this transaction gets a timestamp of 8.
Well, it got one of 6 initially, but once it starts coordinating with the other one,
It
I
changes
think I'm
its-
making up stuff. So
Does it
Yeah,
change its timestamp?
well, I guess. Yeah, the top one.
we should maybe listen to what he said again because I don't know what I'm talking about.
Yeah, S sub. I can't read the letter, the subscript for the top one.
So this is TC, SC, TP, SB. So this top one, the subscript is C.
C, and then the bottom one's S sub what?
I was too
P.
busy laughing about the premise of this.
Oh, apparently those are, special times
Okay, so if we go back
because
to
they
paper,
have subscripts, and then the latter, like S equals 8, is the same as the one at the bottom. There's a white arrow going up, so I guess it changed its time from 6 to 8
and that
because of the one down there.
I'm not quite understanding because I don't see that in the paper, but it doesn't mean it's not true.
Okay.
So yeah, S sub I is the commit timestamp that was picked. That falls between E start and E commit.
Well, let's move on.
Well, this
Regardless,
is our last part. It's just
if you want
Oh,
to
okay.
wait
yeah.
until both of those things are done, you've got to find the latest time that either of them could have been done and wait a little bit past that before you start the next thing that you want to be after.
Okay, quick vote. Go back and listen again, grok this example, or move on.
Let's move on.
Move on. Okay. So moving on, I don't know much more of what was in this section because I got lost about here, and so I kept going and going. Okay, I guess I get this. So, like at a high level, they talk about this is read-write transactions. There are read transactions, read-only transactions.
Yeah.
That
So this is why they do all this stuff. So this, if all they did was 2-phase commit on top of Paxos, that's a system that'll work, right? Like you've got, so you have Paxos, you have a cluster of nodes that will make some sort of decision in a robust, resilient way where you can survive failures, right? So there's a Paxos cluster. The trouble is all of the Paxos clusters need to have, certain properties, and it's useful to have multiple Paxos clusters instead of just having all the nodes be part of the same Paxos cluster, because then, geez, that's a terrible thing.
Yeah, I wonder if building a two-phase commit on top of Paxos would actually maintain the better availability guarantees of Paxos. In the distributed systems Slack, just yesterday, they posted about how Gray and Lamport proved that two-phase commit is equivalent to Paxos, where the number of acceptable failures is 0.
Sure. Yes.
So, like, would that higher availability guarantees be maintained doing a two-phase commit on top of it? As a protocol,
I think so. I mean, the chances of having like a whole Paxos cluster go down.
I mean, in the end, it's all about you're increasing the probability that it's not going to fail.
But you also,
any of these things are there's a possibility that everything could go down, and then you're stuck.
You don't just want to throw everything into the same Paxos cluster, for instance, because there's a ton of overhead and scaling for every node you add to a Paxos cluster, right? There's like
n squared messages.
Yeah, right. So you don't want to have just a bunch, everything in one Paxos cluster. So having this sort of like layer of something on top of Paxos clusters sort of adds a lot of benefit. But in the sense that those Paxos clusters already survive failures, you probably don't really need a bunch of stuff on top of it. But anyway, this is like my high level understanding of Spanner, is that you have writes essentially going through something like two-phase commit on top of Paxos. And then writes are all happening with all this sleeping, and you ask yourself, why is this sleeping happening? And so they have these sections. They do read-write transactions, where we've basically walked through how a read-write transaction works. But read transactions have an additional benefit. Because all of the write transactions are doing this thing where they're sleeping to make sure that the event has passed, the read transactions only have to check the TrueTime API and then just go talk to some nodes. They can bypass doing two-phase commit entirely, right? They can bypass all sorts of properties about waiting for message passing, waiting for a consensus, or anything like that. And so all of these reads can just go straight through and just do the read after just sleeping. So like you say, I want to do a read, it picks a timestamp, and then it just waits until amount of time has passed that it can just go ask the nodes, hey, tell me what you have. There's a read snapshot mode that Spanner has that you basically get for free. Essentially you say, hey, give me the value at this timestamp. If that timestamp hasn't passed already, then you just wait. Otherwise, if it's passed already, you just go read it. So reading previous snapshots is actually the cheapest thing you can do in Spanner. You just go read the previous values at whatever timestamp they had. And so because you get snapshots, because you have read-write transactions, and because the reads are externally consistent with the read-write transactions, but fast because of the TrueTime thing, it actually ends up being fairly straightforward to build something like ACID style semantics on top of. So
this was another thing I didn't totally grok. They talk about these are separate kinds of reads.
Yeah.
You have a read-only transaction and a snapshot read.
Yeah.
So the read-only transaction guarantees that I'm in this transactional order that we picked.
Right, and you can do that just by sleeping. You just pick a time, and then you just sleep, and then you go read.
At that, right, sleep to make sure that the true time range has passed.
You sleep to wait until that snapshot has been created. As soon as a value at that timestamp has been written, right? Like if any value comes in after the timestamp, then that write has come in after your transaction. And so the external ordering says that you won't see that write yet. So essentially you're reading the snapshot at the time when you created the timestamp when you went to go do the read.
So isn't that what a snapshot read is?
I think, maybe I'm not understanding the...
So what's the difference between a snapshot read and a read-only transaction?
My assumption, this is me talking out of my rear again, but...
Which is better than me having
No.
barely read the paper. and trying to
Honestly, I
understand.
don't know that talking out of your rear is better, but,
Is the paper seem too short?
huh?
It's pretty short.
It's a good 8 to 10 pages.
It's-
I mean,
it's-
dense.
It's dense,
Very
it's a
dense.
thick paper, yeah. I guess my understanding of my last time I read through this was that you could essentially implement normal style reads as snapshot reads, but maybe there's an optimization that I'm missing. Yeah. Who knows? In fact, I probably have just explained Spanner, a completely different system that we should all go build. That's not what Google has built.
Cockroach 2.0?
Yeah.
Sweet. Does anyone else understand that better? The distinction between these snapshot reads and timestamp read-only transactions? Sorry, no timestamp.
Oh, I got a name for it. We'll call it Spammer.js.
No.
Okay, well, I didn't
No
either.
JS.
I didn't grok this from the paper, but what I understand is that a read-only transaction is a transaction that comes in that transaction log, whereas a snapshot read can be provided. Oh, and so the read-only transaction, the server picks a timestamp.
Okay, so the difference between a snapshot read and a read-only transaction is that you do have to go ask a Paxos group for the
For a
last
read-only.
committed timestamp. So the Paxos cluster has an idea of what the last committed timestamp was, and so that's the timestamp that you know that no writes have happened since then. So you can use that timestamp for your read. So
in
there
a,
is
in a read-only transaction.
yeah. So you do have to go talk to the Paxos cluster to figure out what that value is.
Okay.
So it's a little bit more heavyweight, but you may not have to talk to multiple servers or
Right.
whatever. Yeah.
Whereas a snapshot read, I just say, here's a timestamp that I want it at, and then I sleep until that's passed.
Well, if it's in the past, like if you're saying give me the thing from like yesterday, then that's almost certainly somewhere easily accessible.
Right.
Yeah.
Okay, cool. There is another presentation that covers much of these same things, and we've beaten lots of it to death, at least at the level that I can understand it at. So if you're interested in that, that was at InfoQ something or other. If you Google InfoQ Spanner, you'll probably find it. Yep. This was another great talk by one of the Spanner team members, so go check that out if you're interested in learning more.
We went to Q conference.